Good afternoon, everyone. My name is Xu Sun. I'm from China University of Petroleum, Beijing. The topic of my presentation is vortex-induced vibration of a cantilevered Euler-Bernoulli beam behind a square cylinder. In past decades, piezoelectric energy harvester utilizing flow-induced vibration of flexible structures have received wide attention due to the increasing demands of power supplement for the low-power electronic devices in various technical fields. A frequently used design is to extract energy from the unsteady wake of a black body utilizing FIV of a cantilevered flexible plate with piezoelectric patches attached to it, as shown in the two figures below. To design pH of high efficiency, understanding the dynamic behavior and underlying physics of a flexible plate behind a black body in cross flow is of vital importance. In previous studies, flow-induced vibration of an attached or detached flexible plate behind a circular cylinder has been well investigated. However, little work has been done on flow-induced vibration of a flexible plate behind a square cylinder. So the purpose of this work is to reveal flow-induced vibration features of a flexible plate attached to a square cylinder using fluid structure interaction simulations. This figure shows the configuration of our model. As shown in the figure, a plate is attached to the lead side of a square cylinder. The cylinder is rigid and stationary, while the plate is flexible and allowed to vibrate in the XY plane. The thickness of the plate is much smaller than its length, and only the in-plane vibration is allowed, so that the flexible plate is modeled as a cantilevered Euler-Bernoulli beam. Moreover, it is assumed that the strain level in the plate is sufficiently small and the plate is inextensible. The geometric linearity of the plate is considered, while the effect of the material damping is ignored. When this cylinder plate body is placed in a uniform flow, vortex will be shed from the cylinder surface as long as the Reynolds number is not too low. Excited by the vortices on the two sides, self-exciting vibration of the plate can be induced. Based on these assumptions, the two-dimensional incompressible and laminar NS equation is taken as the governing equation of the flow domain, and the nonlinear Euler-Bernoulli beam equation is taken to describe the vibration of the flexible plate. An in-house fluid structure interaction solver is proposed for this problem. In the flow solver, a modified CBS scheme is coupled with the dual-time stepping method and the semi-torsional spring analogy method. In the structure solver, the finite element method is used for spatial discretization, while the generalized alpha method is employed for temporal discretization. Finally, the flow and the structure source are coupled by the weakly coupled partitioned method. Using the numerical method proposed, flow-induced vibration of a flexible plate attached to a square cylinder is studied. The parameters in our simulation are as follows. The Reynolds number with respect to the side length of the square cylinder is 100. The density ratio of the plate equals to 84.75. The dimensionless thickness of the plate is fixed at 0.06. To study the effect of the plate length, three plate lengths are considered, 0.5, 1, and 2, and the elastic modulus of the plate varies in 5,000 to 500,000. This figure shows the computational model of our simulation, and this figures shows the mesh we used for simulation. As shown in this figure, the grease around the cylinder and the plate and in the wake of the cylinder plate body are refined to capture the vortex structures in these regions. These figures shows the transverse response at the free end of the plate. As shown in the first column, when the plate is very short, the natural frequency of the plate does not interact with the vortex shedding frequency in the parameter range we considered, and the vibrating amplitude of the plate is very small. When the dimensionless plate length increases from 0.5 to 1, the first natural frequency of the plate interacts with the vortex shedding frequency near this point. And in this region, the vibrating frequency of the plate began to lock to the natural frequency. Meanwhile, the vibrating amplitude of the plate is increased a lot in this region. This means that near this region, the lock-in phenomena appear. At the plate length of 2, both of the first and the second natural frequency of the plate interact with the vortex shedding frequency. As shown in this figure, in this region and this region, lock-in appears, and the vibrating frequency of the plate is locked to the natural frequency, to the first natural frequency and the second natural frequency. Meanwhile, the vibrating amplitude is also increased in these two regions. For long plate lengths, another interesting phenomenon is also observed, as shown in this figure. When the elastic modulus decreases below a critical point around this point, the plate no longer oscillating with the center line, but deflect to the lower side, which means that the symmetry of the response of the plate is broken in this region. This figure shows the instantaneous deflections of the whole plate. As shown in the first row, at a plate length of 0.5, the response of the flexible plate is very small. At plate length of 1, the flexible plate experiences large-scale oscillation of first mode in the lock-in region. At plate length of 2, the plate always deflects downward in the off-central region, and the response is dominated by a second mode-like bending motion. Outside the off-center line region, the first mode dominates the response, and in the first natural frequency lock-in region, large-scale response of the plate is also observed. This figure shows the instantaneous flow fields around the cylinder plate body at a plate length of 0.5. Because flow-induced vibration of the flexible plate is very weak in this case, the flow field around the cylinder with a flexible plate is very similar to that with a rigid plate. At a plate length of 1, however, the case is different. As shown in the third row of the figure, in the lock-in region, the vortex is shed into the wake in advance before it grows up due to the large-scale oscillation of the flexible plate. Out of the lock-in region, the response of the flexible plate is very weak. Therefore, the flow field around the cylinder with a flexible plate is similar to that with a rigid plate. This slide shows the instantaneous flow fields at a plate length of 2. As shown in these 3 rows, in the off-central region, the plate always deflects downward, forming a large-scale stable vortex below the plate. The vortex below the plate is not shed into the wake. On the upper side of the plate, a large-scale vortex is formed and shed into the wake with time. In the first natural frequency lock-in region, the large-scale oscillation of the flexible plate also advances the vortex shedding process. In other regions, the response of the plate is very weak. Therefore, the flow field around the cylinder plate body is similar to that with a rigid plate. Based on the numerical results provided above, the following conclusions can be summarized. Because of the time limit, I will stop my presentation here. Thank you very much.